Hi everyone. So in this video, we're going to go ahead and start to talk about gases, their properties that you make them. Hi everyone. So in this video, we're going to go ahead and start to talk about gases, their unique properties that distinguish them from solids and liquids. We're also going to talk about pressure and temperature as they are two key concepts when thinking about gases. So first of all, temperature is a measure of the average kinetic energy of the particles in a substance. So within any substance, you're going to have a mixture of particles moving at different speeds. Some will be very fast, some will be very slow, but we want to think about the average. So substances that have a higher average kinetic energy will be at a higher temperature than substances that have a lower average kinetic energy. Now there are three different temperature scales, and you've probably heard of these before. The first two are relative temperature scales. So Celsius is based upon the melting and boiling points of water. Fahrenheit is based upon the mixture of ice, water, and ammonium chloride, and that's how we get the 0 point for the Fahrenheit temperature scale. So these are what we use most commonly. In the US, we use the Fahrenheit system. Overseas, they tend to use a Celsius scale. However, they're not great choices because you don't have typically these standards around for you to see them. You don't typically have ice and water readily accessible, or a mixture of ice, water, and ammonium chloride. So scientists came up with something called the Kelvin temperature scale, and this is based directly upon the average kinetic energy of the particles and the idea of absolute zero. So absolute zero is a temperature when it is so cold that all kinetic energy stops. The particles aren't moving anymore, so the kinetic energy is zero. So here you have a table of different values. The ones that are grayed out, I don't want you to remember them at all. But the ones that are white, try and get those stuck in your memory a little bit. So as I said, the Kelvin temperature scale at absolute zero is based upon the idea of it being zero. Celsius, it isn't. It's based upon the freezing point of water. And even though ice is frozen, the particles are still vibrating. Don't forget about that. So absolute zero in the Celsius scale is minus 273. And then the Fahrenheit scale is 450 minus 459. Again, don't worry about memorizing the Fahrenheit scale. The melting or freezing point of water, 32 degrees Fahrenheit. For Celsius, it is 0. For Kelvin, it's 273. Room temperature in Kelvin is about 296. Room temperature can vary depending upon who you talk to. In Celsius, it's about 23, and then about Fahrenheit, it averages around 73. So for body temperature in Fahrenheit, it's 98.6. Celsius is 37. Kelvin is 310. And then boiling point of water in the Kelvin scale is 373. Celsius is 100, and Fahrenheit is 212. So as I said, don't worry about Fahrenheit. It's just kind of a weird temperature scale we use in the US. You will never use it in science. You'll either use your Celsius or the Kelvin scale. So if you look at the difference in values between Celsius and Kelvin, you're going to see they're always different by a value of 273. So that is important for when we are doing conversions. So if we want to find Kelvin when we're given temperature in degrees Celsius, we're going to add 273. Now technically it's 273.15, but we tend to ignore that decimal contribution. To find the degrees Celsius, if we have the temperature in Kelvin, we go ahead and subtract 273. So let's go ahead and try two quick examples. So if it's 20 degrees Celsius, how warm is it in Kelvin? Well, I'm going to add 273. So 20 plus 273 is 293 Kelvin. So pretty warm. And then if it's 300 Kelvin, how warm is it in Celsius? So we're going to subtract 273 this time. So 300 minus 273 is 27 degrees Celsius. So as I said earlier, at absolute zero, this is a theoretical temperature where all motion stops and kinetic energy is zero. Now, in scientific labs, we have gotten very, very close to absolute zero, and we do see that the motion slows so far down. But we haven't yet managed to get to absolute zero even in a lab setting. So it's still a little bit of a theoretical idea there. Otherwise, as temperature then increases from absolute zero, the kinetic energy, and therefore the amount of motion of the particles, will also increase. The molecules can move around in 3 different ways. The first is what we call vibrational. So this is where the covalent bonds between 2 atoms, they're going to stretch, they're going to bend, they're going to move, kind of like if we had springs attaching the different atoms together. Rotational is where the particles are basically just spinning around in their center of gravity. And then translational, this is where the particles are actually moving left and right and forward and back. So if the kinetic energy of the particles becomes greater than the intermolecular forces holding the different particles together, remember, intermolecular forces are between 2 different molecules, then the substance will undergo a phase change. So it's going to go from a solid to a liquid or a liquid to a gas. Okay, so let's think about gases and what makes them unique. So gas particles are in constant random motion, and they will continue to travel in the same direction until they either collide with another gas particle or with the edge of the container. Gases are unique from solids and liquids in that they are able to be compressed a lot. So you can take a gas from a big area and compress it down to a small area. Gases will expand to fill their container, and they have much lower densities when compared to solids and liquids. Okay, now, so pressure. Okay, pressure is the force applied per unit area. So in gases, collisions with the side of the container is what creates the pressure within that container. As the number of particles increases, if the temperature and volume is held constant, the pressure of the gas increases because there are more collisions. So if you have a tire on your bicycle or on a car, you know as you go ahead and add more air into it, the tire pressure increases. That's because we're having more collisions. Okay, if the size of the container decreases, the pressure will increase because the collisions will again occur more frequently because there's less open space. So pressure is also related to the area. So this is the idea of if you take a balloon and you try and squish it down, you might have to push it in a little bit, but then eventually it gets harder to push it closer together because the pressure has increased. So let's go ahead and do a thought question. So on Monday, I wear a pair of high-heeled shoes. On Tuesday, I wear tennis shoes. How does the pressure I exert on the earth compare for the 2 days? And how does the force that I exert on the earth compare for the 2 days? Well, if we think about it, on Monday when I wear the high heels, there's much less surface area, so my weight is going to be over a smaller area, so the pressure is going to be higher on Monday and lower on Tuesday. However, the force is going to be the same the 2 days because my weight will basically be the same the 2 days. Okay, so here I have a quick demo video. I will show you that a little bit later. But the idea is that pressure from weight is directional. So it goes directly to the center of the earth, but pressure from a gas is felt in all directions equally. So this lets us do a really cool thing with a glass of water. So let's go ahead and I'll send that video out later. Okay, so it's really important that scientists are able to measure the pressure because sometimes that can affect how reactions run. Now, one of the kind of key ideas or key tools for measuring pressure comes back to the idea of a manometer. So a manometer is a U-shaped tube, and I have a picture of it here. And then on one side, we fill it with water, and the other side, we fill it with ethyl alcohol. Now, a really interesting thing happens in that the side with the water will be lower than the side with the ethyl alcohol. Okay, so the water will have a height of 100 centimeters and the ethyl alcohol will have a height of 127 centimeters. The reason why this is the 2 different liquids have different densities, so we need to equalize the pressure on both sides. The way that we do that is by having different column heights. Okay, so to have them both have the same pressure of 100 grams per centimeter cubed, I need to have different heights because they have different densities. Because ethyl alcohol is less dense, we need more of it to equal that 100 grams per centimeter cubed. So this comes down to the idea of mercury, okay? So mercury is the most dense liquid we have. So when we use mercury in our measuring tools like barometers, it allows us to create smaller tools. So we don't need to have ones that are meters tall. We can have ones that are much more reusable in size. That makes these tools more portable. So one of the key tools that we actually use for measuring pressure is a barometer. And you probably hear about like the barometric pressure if you watch the news or the weather, things like that. So traditionally, as I said earlier, mercury is used as a column because it allows us to have a shorter tool. At sea level on a typical day, the column of mercury will be 760 millimeters in height. And that's a really important number that we'll get to later. So this was what was traditionally used. Now mercury, although it's better than water that you can have smaller tools, it's not great to have around because it can be toxic if you get too much of it inhaled, things like that. It's also, you're still dealing with a liquid, so it's harder to transport. So modern day barometers use a metal spring instead to detect changes in pressure. So remember that number 760 millimeters? Well, that becomes an important value for our conversion factors. Okay, so here I have different units of pressure that we can relate. So we have 1 atmosphere, which is the value at sea level on a typical day, is equal to that 760 millimeters of mercury. So that's where that comes in. We can also use a unit of torr, which has the exact same value as millimeters mercury, or we have units of pascals and kilopascals. And then finally, in the US, since we like to use pounds and inches, we have pounds per square inch, or PSI. So these are some important conversion factors for pressure that you will be able to use throughout this unit. So make sure you keep this list handy in your notes. And let's go ahead and try some conversion problems. Okay, so let's go ahead and try these 2 different conversion problems. So the first one, I am given the unit of ATM, and I am asked to find the pressure in millimeters of mercury. So just like always, I'm going to set my factor label table. My given, 0.830 atmospheres, that is going to go into the first spot. Okay, and then because I need my units to cancel on the diagonal, if I have atmospheres up top, I need the unit of atmospheres on the bottom. And then the unit I am trying to get to is millimeters of mercury. So that's going to go up on top. Now, in order to fill in the numbers for these 2 units, I'm going to look in my notes to find the conversion factor. So if I look in my notes, I see that 1 atmosphere is equal to 760 millimeters of mercury. Okay, so then numbers on top, I go ahead and multiply those together. Numbers on the bottom, I divide by those. So let's go ahead and plug this into our calculator. Okay, so we have 0.830 times 760, and then technically divide by 1, but that doesn't change anything. So that is the answer my calculator spits out. But we need to go ahead and think about sig figs. Okay, so we're going to focus on our given as always to figure out how many sig figs we have in that number. Remember, leading zeros never count. Trailing zeros count if there is a decimal, which there is for this problem. So that means I have 3 sig figs in my given, so I want to round my answer to 3 sig figs. So I'm going to chop off the 8, and because it's greater than 5, I round that up to 631 millimeters of mercury. Okay, so for the next problem, I want you to go ahead and try it on your own. So pause the video, try it on your own, and then come back and we'll talk about the answer for that one. Okay, so let's go ahead and solve this problem now. This time we are given the units of millimeters of mercury, and we are being asked to find kilopascals. So just like before, I set up my factor label table. My given, which is 631 millimeters of mercury, goes in the first spot. Because I need my units to cancel on the diagonal, if I have millimeters of mercury up top, on the diagonal, I'm going to have millimeters of mercury. And then the unit I am being asked to find is kilopascals. So now I'm going to look in my notes to find the conversion factor for this. So in my notes, I see that 760 millimeters of mercury is equal to 101.325 kilopascals. Okay, so make sure you're getting the kilopascal value and not the pascals or anything else. So again, numbers on top we multiply, numbers on the bottom we divide. So 631 times 101.325. And then we're going to divide that by the 760 that's on the bottom. So that gives us an answer of 84.1. Okay, and again, we're going to round to 3 sig figs because that's how many my given has. So 84.1, and then finally, don't forget your unit to get that final answer. So I hope this helps. If you have any questions, please let me know. Otherwise, have a great day, everyone, and I'll see you later. Bye.